Hello and welcome. In this video we're going to take a look at exact solutions for general first order ODEs. We recall that we looked at linear ODEs, which had this structure, dy dt equals some function of t times y plus some other function of t. Now this is not always going to apply. Here we assumed that this function was linear in y, but not all have to be that way. So in general, we may be faced with equations that look like this. And the first difference that we should pay attention to is this fact that this function m can also depend on y. It could be some function of y, as well as the coefficient in front of the y prime, or the dy dt. So this looks like a funny form, but you can always rewrite the equation into this form. So that you can observe what these functions are. Now, of course, there'll be instances where these two functions only depend on t and therefore start to reduce and look more like this first order ODE, but this covers all of our bases here. And so m and n can be any functions of t and or y, which means that there could be a y squared or a y cubed or a sine of y or any nonlinear function of y altogether. And we have to set equal to 0 just because we've moved everything to one side. It's convenient to write it this way. We don't write these terms like we did here, a of t, y, because the function may be nonlinear, so it could have a y squared or a y cubed. We just don't know what function of y we're going to be dealing with. So we let this sort of a of t, y thing be handled by this m function. We do not attempt to write it in a similar form as the FOLDE, again, because m of ty could very well be a nonlinear function involving y. So let's take a look at just one that's not in this form and see how we can get it into the correct form. So what are m and n for y prime equals negative 1 over y minus y over 2t? So there are multiple ways to get it into this form. What I'll go ahead and do here, remember this is just dy dt, so we can leave it as y prime to keep our writing simpler. And what I'll do here is I'll get a common denominator, and the reason I'm going to do that is because then I can multiply both sides by something to help me cancel out the components. So if in the first fraction here, negative 1 over y, I see that the common denominator here is if I multiply this fraction top and bottom by 2t, and I multiply this fraction both top and bottom by y, I'll be able to get it into that correct form. So here I'll multiply by 2t on top and bottom. In the second term, minus y over 2t, I'm going to multiply top and bottom by y. So what that will do is, in this first fraction, I'll have negative 2t over 2ty, and in the second fraction, I'll have negative y squared over 2ty. So now because I have common denominators, I can add their numerators. So I'll have y prime equals negative 2t minus y squared all over 2ty, and now I can multiply both sides by 2ty. Again, because remember what I'm trying to do here is get it into this form where I have some coefficient multiplying the y prime and then some standalone term not involving dy dt. Okay, so now when I go ahead and see what I have left, I have negative 2t minus y squared, and if I add both of these to the other side, I'll have 2t plus y squared plus this second term, 2ty y prime, equals 0. So now I can very easily identify what m and n are, and m is just going to be everything that is not attached to the y prime term. So here I will have this guy right here. This whole thing is what we're going to call m of t comma y. And this other thing here is what we are going to refer to as n of t comma y. So you can see that we can rewrite this equation, this nasty looking equation, into this, and this is definitely nonlinear because I see that first of all I have a y squared in here, and this a of t, notice that this depends on both t and y, so it's not just an a of, I can't call it n of t since it has y in it as well. Same thing goes for m. So now that we have that, we want to make an observation. We don't really know how to solve this. This didn't give us any insight into how to solve this equation, but let's make a couple of observations here. So if we looked at this equation and now we see that m is this, and if I were just to happen to compute its partial derivative, so the partial with respect to y of 2t is 0, and the partial with respect to y of y squared is 2y. And to do the same thing for n, if I take the derivative of n with respect to t, the other variable, then if I take the derivative with respect to t, 2 and y, 2y is a constant, so the derivative of t is 1, and I'm left with 2y. And of course, the thing that we see is that these are equal. When are partial derivatives equal? Well, based on the equality of mixed partial derivatives, we're beginning to think that m itself is already the derivative of some function with respect to t, and that n is already the derivative of some function with respect to y. Why am I saying that? Well, if m itself is the derivative of some function with respect to t, and you take the derivative of that with respect to y, you get the mixed partial derivative of that original function. If n is already the derivative of that same function, but with respect to y, and now we're taking the derivative with respect to t, we're getting another mixed partial derivative. So let's call that function that we're this sort of esoteric function that we don't know much about. Let's call this guy psi. So this is psi, is that Greek symbol right there, to be some multivariable function. And the reason we're using Greek letters here is just because these are more easily thought of as helper functions. They're going to help us do something. So we're kind of introducing them into an equation where they don't belong. So using Greek letters just reminds us about that fact. So we're arguing here that if these two are equal, then maybe they're the mixed partial derivatives of some function called psi. That is, we said m is already the derivative of some function with respect to t. So there's some function, its derivative, with respect to t. And that n is already the derivative of that same some function with respect to y. So n is the derivative of psi with respect to y. Therefore, if we take the derivative of m with respect to y, well, m is the derivative of psi with respect to t. So if you take the derivative of m with respect to y, well, m itself is the derivative of psi with respect to t, and therefore this comes out to be the second derivative of partial y partial t. And then if you take the partial derivative of with respect to t of n, well, what is n? N is the derivative of psi with respect to y. So that means that this comes out to the second derivative of psi with respect to t with respect to y. And since these are mixed partials, they should be equal. Now we're just making some speculation here. We're not saying this is always going to be true, but we're making an observation that it was true in this case. If it's not true, well, maybe we can try to figure out how to get it so that they are, m and n are some partial derivatives of the same function. Okay, so instead of writing this long Newtonian notation, we're going to use this compressed notation. So we know that psi sub ty is equal to psi sub yt, based on the equality of mixed partials. So this means that in my equation, m of ty plus n of ty times dy dt equals 0. If m is the derivative of some function with respect to t, I'm going to replace that as d psi dt. And if n is already the derivative of some function with respect to y, then I can replace that with d psi dy. And then multiplied by dy dt. So notice the dy's cancel and you get d psi dt plus d psi dt. This is where the multivariable chain rule comes in to help us out a little bit. We're just building towards working for a solution, but we keep making some substitutions and such. So from the multivariate chain rule, it turns out that this left-hand side is actually the derivative of psi with respect to t, derivative with respect to t of psi. Let's draw a diagram here, this chain diagram, to help us see this. So here's this psi function, and psi depends on y. And because of the structure of differential equations, we know that y itself is the solution to our differential equation, and that depends on time. And then potentially psi depends directly on time as well. So we're going to have three partials here. We'll have d psi dy, and then dy dt. And then the direct dependency of psi on t will be the partial of psi with respect to t. And you see that d psi dy times dy dt is this term, and d psi dt is this term. So by definition, the derivative of psi with respect to time of this psi of ty function is equal to d psi dt plus, following the opposite chain, we have d psi dy times dy dt. And what that allows us to do is we're allowed to now make a mathematical substitution. Anywhere I see this, I can replace it with this. So I'm going to do that. I'm going to replace this whole left side right here with the derivative of d psi dt. Well, that's pretty cool. So that means that now I've reduced my entire equation that started off as m plus n times dy dt equals 0 to the derivative of some function equals 0. Now the beauty of this is that if you integrate with both sides with respect to t, this is like the reverse product rule that we often see in integrating factors and the derivation of that process, that when you take the integral of a derivative, you're just going to get psi of t comma y. And the integral of 0 is just some constant, because remember, we have to say, well, the derivative of a constant is 0. So the integral of 0 is some constant, potentially, which could be 0. So then we end up with psi of t comma y equals c, and right away you'll notice this no longer has any derivatives in it. Therefore, this would be the solution. And if psi could be solved for y, then we have our direct solution. Otherwise, we can leave it as an implicit solution. So if this is too hard to solve for y, you just leave it as what we call an implicit solution of y. That just means that it has to stay that way. It's still a solution, but it's not necessarily in the form that we want it to be, like y equals